Okay, round 2 on this, hopefully without the mistake. Okay, quickly recap on why equating coefficients work. Since you're very young, you're taught you can't add apples and pears together and get anything sensible, because pears and apples are different. The same thing is true with types of terms. You can't add an x cubed term to an x squared term because they are expressly different. That's what you're familiar with. So with this we could multiply it out to give us 2x cubed, and of course I'm going to multiply in. The reason for multiplying in is if there's a minus here, people often make a mistake and lose the minuses. So we do 6x squared plus 3x, and that is equal to ax cubed plus bx squared plus cx plus d. And if we wanted to work out what a, b, c and d are, we create the terms. So we've got a 2x cubed, we've got a 5x squared, we've got a 3x, and that's equal to these terms, which actually tells us that a equals 2, b equals 5, c equals 3, and d equals 0. And one of the reasons we do these sorts of things is these separate terms are nice and predictable, so we can do things about predicting graphs and graph sketching with it. It's a lot easier to graph this expression, the 2x cubed plus 5x squared plus 3x, than it is these brackets separately. So it's not about simplifying expressions. We are now trying to divide them to see what things are happening. So let's move on to the tricky one. So my first example, I'll do that to the top just in case I can actually get it to work. So example 1. That was, we want to do x to the 4 minus 5x squared plus 2, all shared by x plus 1. And we know that we can try doing this division. What's going to come out at the end of it is the question. Now, if you were to think about very large values of x to the 4 is considerably bigger than 5x squared, is massively bigger than 2. So at very big values of x, we've got x to the 4 over a very big value of x compared to 1 is a big value of x. So the order 4, the greatest order in the index in the top, this actually says the order of this expression is order 4, the whole of it. So this whole expression is order 4 because of that. The whole expression here is order 1. And when you take an order 4 and divide it by order 1, you wind up with an order 3. So we know that the highest power we can expect to come out in our answer is a cube term, but we don't know the coefficient. Then as we come down, other powers, the x squared power, they start making all the little adjustments for intermediate values. So we get bx, and we get a bx squared plus a cx, and plus a d. So if this graph didn't have a denominator, we could create some form of special cubic graph. Now we could stop here if we knew that x plus 1 was an exact factor of x to the 4 minus 5x squared plus 2. Looking at the numbers, I know they don't. That means that there could be a remainder term. So what we're going to have is a remainder function on the end. And the remainder, in this case, because it's an x plus 1, it's an order 1 denominator. All we have is a remainder e, and what do we normally do with the remainders when we've done a division? We put them over the thing we were dividing by, the denominator again. So with an order 1 we only have a number term in here. We'll talk about the other in a minute. So now we've done this, we can multiply through. Now the advantage with multiplying through on these forms is we know these two are going to cancel. So this becomes a function ax cubed plus bx squared plus cx plus d, both of which need to be multiplied by x plus 1, and then added. E times x plus 1 divided by x plus 1 is just e. And in doing this, multiply both sides by 1. Sorry, I forgot to put the numerator on this side. Because the denominator's changed. We can say these two things must be equal, with one thing to be careful of. We have no idea what happens when x plus 1 equals 0, because that's a denominator, and that can lead to x is not allowed to be negative 1. So we can't say what happens when x is minus 1 directly. You can actually put things in and see what happens, and we get a number over 1, which suggests to me that it's going to go off to an asymptote, go off to infinity. So now expand the bracket on the right hand side, so we get ax cubed times x, which gives me ax to the 4, and ax cubed times 1, which is ax cubed. So that's the first lot, that's line 1. Line 2, I'm going to multiply the bx squared times x. So bx squared times x is an x cubed term, so I'm going to line it up with the x cubed term I've got. And add to that a bx squared term. And add on to the end of it the third line. Cx times x is cx squared. Add on cx times 1 is cx. And we're left with the d. So d times x for the fourth line, d times x plus a d, and then we've also got the e part that came from my the remainder. Now the reason I've lined these up is it's easy to see the vertical sums, and I'd rather use space to make things clearer. Do tell the examiner that you're equating like terms or equating coefficients. So x to the 4 tells me that 1 is equal to a. X cubed, well, there is no x cubed here, so it's a factor, its coefficient is 0, and that's a plus b. A is 1, so we now know that b is minus 1. X squared is minus 5 and is equal to b plus c. Well, we know b is minus 1, so that means c must be minus 4. And x, no term, so that is equal to, the x term is c plus d, c is minus 4, tells me that d must be 4. And last bit of line for this one, number term. This is at the point where I realised I'd made a mistake, is I didn't have a number term to calculate. The number term 2 is d plus e. And that leads to e. So that's got a 4 on it. So that leads to e being minus 2. And my final expression, therefore, is my a, which is x cubed, plus the b, so minus x squared, plus the c, which is minus 4x, plus the d, which is 4, minus 2 x plus 1 is the result of that division.